I wore this shirt deliberately because we are talking about fair division today and dividing things up. So Williams has how many neighborhoods? As of now, 4. Yes, that may change, but as of... I'm sorry? They keep changing. So my daughter was wondering about what I was doing, and so she added some notes for me. So in today's lecture, it may be useful to know that I think it's 30 plus 30 equals 60, and 500 plus 500 equals 1,000. So Kayla just thought that that would be useful information to know. Okay? Okay. So in a stunning squeaker, in terms of should we do the analysis discussion today, it won by 1 vote, 1-0. So this shows you the importance of voting. Okay? Analysis for Sperner. We are going to do it. It won by a vote of 1-0. If you did not want to do this, if you had voted, you could have changed things. It's too late to vote. The polls have closed. No, it is too late. It is too late. No, it is too late. We're moving on with class. And so, again, when you have opportunities in life to control things, take advantage. When I was a graduate student, one of the things we all prepared for is if the professors ever gave us an opening on an oral exam, we were ready. So, what's your favorite result in complex analysis? This is an opportunity to steer the conversation to something you like. Oh, I don't know, I like everything. Oh, then the professors are like, you always want to have a way to control something. If somebody asks you, what was your favorite class? What was a moment where you were challenged? What was a mistake you made that you learned from? You want to have something ready to go. So we'll do the analysis review quickly. So the main result we need is what's called the Bolzano-Weierstrass theorem. And basically it says if we have a sequence in a closed bounded set, then a subsequence converges. Proof by pictures. Let's take a one-dimensional case. So here's the interval 0, 1. We have some sequence x1, x2, x3, x4, and so on and so on and so on. We have some sequence of points in here. And the proof goes as follows. So let's see if I can. A subsequence of the sequence converges. So for example, if I look at the sequence -1 to the n plus 1 over 2, does that sequence converge? So if that's my sequence, does this sequence converge or diverge? Diverges. So we get, when n equals 1, we get 0, then we get 1, 0, 1, 0, 1. Diverges, but a subsequence converges. There's actually infinitely many, there's even uncountably many subsequences that diverge. 2 of them are screaming at you right now. Right? Which 2 are screaming at you? All zeros and all ones. Right? Evens converge to 1. Odds converge to 0. Here's another one. The primes converge to 0. There are infinitely many primes. Only one prime is even. All the other primes are odd. So if I just restrict myself to prime indices, this is going to converge. Okay? What we have here is we have a general principle. Whenever you have a sequence that's basically restricted to a finite region, to a bounded region, and the region is closed. So closed means it attains its limit points. If I study, xn equals 1 over n on the interval 0, 1, notice I'm not including the endpoints. Does this converge? Yes. I was not able to trick you. Excellent. Yes. It converges. Does it converge to something inside the open interval 0, 1? No. Doesn't converge to something in the interval 0, 1. So one of the problems is you could converge, but not to converge to something in your space. That would be extremely bad. Now, fortunately for what we're doing, this is never going to happen because we always consider maps from our space to itself. And so we're always going to be dealing with closed sets. So a closed set is a set that contains all its limit points. You never have to worry about leaving your space. All right, so I'm going to give you a quick proof now of the Bolzano-Weierstrass theorem. So we have infinitely many points. Here's 0, here's 1, here's 1/2. Let's split our interval into two parts. Could we have only finitely many in both halves? So what would happen if we had finitely many in both halves? Yes? There are, but that's not answering the question I just asked. If we only had finitely many in both halves, what would happen? We only have finitely many points. We have infinitely many points in our sequence, therefore one of the two halves must have infinitely many. What do we do with the point 1/2? What should we do with the point 1/2? Is it in the first interval? Is it in the second interval? Is it in its own interval? Does it not matter? Is it in both? What should we do with 1/2? We can put it in either. So we could always put it in the second one. We could always put it in the first one. We could even put it in both. Is it possible both intervals have infinitely many points? Sure. All we need is that at least one has infinitely many points. So at least 1/2 has infinitely many points. Now it's time for lather, rinse, repeat mathematics, right? So let's say that there were infinitely many in here. We now break this in half. And now there must be infinitely many in either the left half or the right half. Let's say it was this half over here. We break this in half. There must be infinitely many. We break this in half, etc., etc., etc. And so we just keep iterating this process. And every time we do this, the diameter, the girth of our set is decreasing by a factor of 2. So what you can always do is you can always look at the left endpoints and the right endpoints at each moment in time. What can you say about the sequence of the ANs, the left endpoints? Do they ever get smaller? No. What about the right endpoints? Do they ever get larger? No. So you would get, A1 is less than equal to A2 is less than equal to dot, 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 is less than equal to B2 is less than equal to B1, dot, dot, dot. And so the bottom endpoints are going up, the top endpoints are going down. But what do you know about the distance between AN and BN? The distance between AN and BN, what is that going to? 0. Well, if the distance is going to 0, then the A's and the B's have to converge to a common number. If they converge to a different number, there would be a separation. And there's no separation in the limit. So this is very close to a rigorous proof that on the line, if we have an interval, if we have a subsequence in an interval, there will be if we have a sequence in an interval, there'll be a subsequence that converges. Could that subsequence converge to two different points? No, if the subsequence converges to two different points, it's converging to here, say, and to here. What's the distance between them? Something positive. And we know the distance is going to 0. So you'll get that there is a unique limit. Okay? So this is the idea in one dimension. In two dimension, it's essentially the same argument. And so I will just show what goes on for the triangle and leave the general case. So we have a triangle like this. I'll divide it like this, because this is exactly what we'd be doing in Sperner's lemma, and all we care about in this class is Sperner's lemma. I now have 4 subtriangles. I have a sequence with infinitely many terms. What can you say? So what do we know? One of the triangles has infinitely many. Any preference as to which one will have infinitely many? Top one. First voice wins. So we divide the top one into 4 triangles. Which one has infinitely many? Top one. Which one has infinitely many? Thank you. Yeah. Well, which one is the bottom? I'm sorry? See, top is a very nice one to say. Top is clear. Left is clear. Right is clear. Top one. This one I'll take the right this time. I'll take the right this time, the left this time. And you can see the convergence happening. And so when we're doing Sperner's lemma, all we care about is that when we have these sequence of triangles that have 3 distinct labels, we just see where does that live. And then we will have infinitely many of these. And then when we do it initially, one of the 4 triangles will have infinitely many smaller subtriangles with 3 different labels. And then we divide that one. One of those will have infinitely many. And we keep going, and we keep going, and we keep going. Okay. Any questions about this? So this was one of the analysis preliminaries we needed for the proof. I want to go through, as long as we're doing stuff on the line, I want to show you another way to prove Sperner's lemma in 1 dimension, which does not generalize. But it is a nice way to prove Sperner in 1 dimension, and it will bring up a concept that if you haven't seen before, it's a good proof technique to be aware of. How many of you have seen proofs by induction? Okay. If you haven't seen this, it's a little bit troublesome that you've made it this far in the math career, but that will be corrected by the time you do real analysis. How many of you have seen proofs by strong induction? Okay, not as many. What's the difference between induction and strong induction? Yes?
You assume it's true for the previous one versus for all the previous ones.
Good. So in strong induction, you assume not just it's true for n, it's true for everything from 0 through n. And then you show it holds for n plus 1. Whereas in induction, you assume it holds for n, and then show it holds for n plus 1. Is there any difference between strong induction and induction? If you're dealing with countable things, no. There's no difference at all. It's just a question of when you're doing the arguments, do you need to use just the previous case, or do you need to use all possible cases? So for induction, does anybody know what the first problem is that you have to prove by induction?
Base case.
I'm sorry?
Base case.
No. The first result that they ask you to prove by induction. What's the first problem they ask you to prove by induction? Nobody knows? The most standard problem to prove by induction. Yeah, 1 plus 2. 1 plus 2 plus 3 plus n equals n plus 1 over 2. That's probably the most standard thing to prove by induction. If they're not doing this, maybe it's 1 plus 3 plus 5 plus 7 is going to give you, n squared. The sum of the odd numbers is a perfect square. How would you do this by induction? 1 plus 2 plus n plus 1. By induction, what do we know about the sum of these numbers? Well, we're assuming it's n plus 1 over 2. So you have n plus 1 over 2 plus n plus 1. I'm going to multiply by 1, one of the most common techniques in mathematics. And now I can combine, and I get n plus 2 times n plus 1 over 2. If I rewrite this, this is n plus 1 plus 1 over 2. That's exactly what we were supposed to show. So this is the most standard proof by induction. And when I'm doing this, I don't need to know that the sum of 1 plus 2 is equal to 3. I don't need to know that 1 plus 2 plus 3 is equal to 6. I just need to know the sum of the first n terms is this. That's the only ingredient I need to use. Yes?
How do you do strong induction?
For this one,
Yeah.
we don't. That's the whole point. This is an example where we don't need to do strong induction. Yeah, 'cause I don't.
Need to use it.
Yeah,
Because it would be
I would.
induction if you just said it holds for one.
Right.
Okay.
Right. This gets into a controversy from the green chicken contest a few years ago, where you were supposed to use a certain result to prove a theorem, and somebody did not use that result, and they just quoted the green tau theorem, which we were pretty sure they did not understand the proof of. Most of us in the room did not understand. In fact, I think no one in the room understood the proof. And do we give them credit? They didn't use the given. In the end, we decided we would only care about this if it would affect who won. And fortunately, it did not affect who won, so we gave them full credit. The green tau theorem says that if you look at the primes, the set of primes contain arbitrarily long arithmetic progressions. So numbers of the form n, n plus 2m, n plus 4m, n plus 6m, n plus 8m. Let's say you want to have an arithmetic progression of length 2 billion. You will find an arithmetic progression of length 2 billion among the primes. It may take you a while, but you will find it. All right, so what I want to do now is strong induction in the one-dimensional Sperner. So what does Sperner's lemma tell us in one dimension? One-dimensional Sperner says what? So what would one-dimensional Sperner be? This is a great way to review what we've done. What is one-dimensional Sperner? Yes?
If there's a line segment and you label everything from 0 and 1, you'll always have something that has labeled on 0 and 1 on one side.
Good. So somewhere in here, we either have a 1, 0 or a 0, 1. And we are only allowed to use zeros and ones. If I was a math comedian, this would be probably good stand-up material. Base case. Okay?
Wow.
Yes. I'll leave that as an exercise. All right. This is not that hard to prove that if you have just two labels, the one on the left must be a 0, the one on the right must be a 1, you will find a 0, 1 adjacent to each other. Okay? Inductive step. I think they still call it the inductive step. I don't think they call it the strong inductive step. So assume true if have k less than equal to n labels, must show true for n plus 1 labels. Turns out nobody commented on this. Sperner's lemma is not stated the way I need it stated.
How is it stated up there?
I didn't write it down because I didn't want to write it down yet. What was stated was that we have an interval 1, 0 and an interval 0, 1. Sperner's lemma is actually a little bit more than just we have an interval. What's the actual statement for Sperner? There's an odd number. So have an odd number of 0, 1. The base case is still trivial. Okay? So now we're going to proceed by strong induction. All right. So we now have 0, 1. So we'll call this our first label, our second label, our n minus first label, our nth label, our n plus first label. And we're going to proceed by strong induction. What are the possibilities for label xn? 0, 1. So case 1, xn equals 1. So in that situation, what happens? I'm sorry?
What you had, like x1 to xn is just xn.
Yep. So we can actually just view it now as 0, 1, 1. And what do we know is going on here? We're now in our previous case. Previous case must have an odd number of 0, 1. Any questions about that? All right, what's case 2? So what would case 2 be? Xn equals 0. 0. So here's xn plus 1, here's xn, here's 0. Depending on what we're trying to prove, we're either done or not done. If our quest is to just find a 0, 1, are we done? Yes. But we're trying to do more than just find a 0, 1. We're trying to find that there's an odd number. We're trying to get more information. If only want a 0, 1, we're done. Okay? But we want more. Want an odd number. Can you begin to see the strong induction now? Can we use, we now have a 0 here and a 0 here. Can we just appeal to the previous case, the case with just n elements? Yes or no? Why not? Because we don't have what? We don't have the previous cases. So the problem here is that we have a 0 and a 0. We want to have a 0 and a 1. So cannot use earlier case as zeros on the end. So what we can do is we can keep going to the left until we get a 1. And so go left until hit a 1. And now it's going to look something like this. Here's 0, here's a 1, here's a bunch of zeros. And now we're in an earlier case. What can we say over here? By induction, we have an odd number of 0, 1. What about in here? How many 0, 1s do we have in here? We have 2. Have 2 0, 1s here. Therefore, we have an odd number total. And this is where we need to use strong induction. It's not enough to look at just the previous case. Is it possible that the one, that we might not have any 1s and we might go all the way back to the beginning? Yes, and if that's the case, then we only have 1 0, 1 here. We don't have 2. So this is assuming the existence of a 1. You've got to be a little bit careful when you are writing this down. So writing it down like this assumes there is a 1. If there wasn't a 1, okay. If never a 1, we have something that's all zeros and a 1, have 1 0 1. Okay? So I really like this because this is a nice way to introduce you to induction, to strong induction. It's a great, powerful technique. What is the natural question you should ask now that we have so successfully done one-dimensional Sperner? Two-dimensional Sperner. Extra credit if anybody can make this work for two-dimensional Sperner. What's the difference between one-dimensional Sperner and two-dimensional Sperner? If I were to try to do this for 2 dimensions, what's the geometry going to look like as I start cutting things up? You know, if I cut something off like this, it's no longer quite a triangle. So see if you can find any way to make an inductive argument like this work for 2 dimensions. And the difficulty is when we're splitting things up in horrible ways. Okay. What I want to do now is I want to talk about the rental harmony paper. So this was the rental harmony paper. And this was by Francis Su. Okay. So can somebody tell me what this paper is concerned with? What is it studying? What's the rental harmony paper studying? Yes.
Like you have a house and have a certain number of rooms that you're trying to rent between two friends. How do you divide rooms?
Good. So how do you divide rooms among people? Another thing it looked at was the cake problem. You have a cake. You want to figure out how do you divide the cake fairly among n people. Maybe different parts of the cake are considered more desirable. All right, I'm going to try to rotate this upwards to see if we can capture this. No, not even close. All right. Who can tell me what this is a map of?
Golf teams.
Golf teams.
Not hockey.
Hockey. All right. So this is data from Facebook. Oh dear, I hope this is still recording.
Oh man, it's literally just the one.
I'm sorry?
We're looking at the teams that have like the one, the Texans, and like
Hey, be quiet.
Wait, is it? Wait. Is the actual fan of the Texans here today?
No, Bills.
Oh, the Bills. Wow. Okay.
I think it's more interesting the
Wait. There's no Jet sections because we're doing NFL teams. Anybody notice anything interesting in the map? There's lots of things.
Broncos are very popular.
Broncos are very popular. It's tough to tell a little bit with the. No, Cowboys in Nevada. So, notice over here. This looks like this is Packer country, I think. Over and through here.
The Cowboys in Nevada.
I'm sorry. But
Alaska likes the Seahawks? All right.
yeah, I was gonna say. No. Who's from California? All right. What do you notice that's interesting about the California fans? The Raiders. Okay? You have this batch of the Raiders out here. The Raiders used to play in Los Angeles. It's been a long time since they've been in Los Angeles. They're now up. Yes. And notice, even in Raiders territory, you don't find Raiders fans.
Well, you don't find many Raiders fans in Southern California either.
No, you don't find many Raiders fans at all. But when you look at this map, one of the things I like about this map is you can kind of view this similar to our partition problems, our rental harmony problems, trying to decide who likes who. Think of this in terms of Sperner's lemma, where we're coloring things by who wins. Is the coloring continuous?
Florida would make up its mind.
Florida has a lot of teams. But so you actually have non-contiguous regions. Okay? This is not good for a lot of mathematical analysis. Okay? Fortunately, in what we're going to be doing, we actually have a much nicer situation where we don't actually have to worry about this. And so what we're going to be doing, it turned itself back on, interesting. It did turn itself off a moment ago, right? All right. I'll physically unplug the computer. That should make a difference. If you think about what we're doing for Sperner's lemma. Why do we care about Sperner's lemma? Why do we care about Sperner's lemma? What is Sperner's lemma designed to give us? Fixed points, right? The whole reason we care about Sperner's lemma is we are searching for fixed points. And Sperner's lemma is designed to give us a fixed point. So we have something, we start off with 3 vertices, 0, 1, and 2. And the way we're going to view this as a division problem is we have some segment, it has length 1. We're going to chop it off at x0, x1. I want to do it this way. No, here, I'll do it this way. I'll do it this way. Here's x0, here's x1, here's x2. I have some block, I have a massive 1, and I'm going to chop it up. The first x0 of it goes to person 0, the next x1 goes to person 1, the next x2 goes to person 2. This is the division. Okay? We're going to assume we have continuous resources, and we just plug all the resources in a line, and we're dividing them up, and the first person gets everything up to x0, the second gets everything up to x1, the third gets the remainder. Is it reasonable to assume resources are continuous? So hopefully you will never have to go into divorce proceedings, but if you do, think back to this class. We saw the clip from the movie War of the Roses. You really cannot divide up a house by putting down tape. My kids now enjoy Pokemon cards, and they understand that if you rip a Pokemon card in half, its value is now gone. Okay? You cannot just divide every resource. And so when you consider the discrete version of this problem, it is significantly harder. And you then have people assigning values to the different objects, and then you can make this into a linear programming problem. How much should each person get to maximize the happiness in the divorce proceedings, to maximize the happiness in the allocation? If you don't like divorce, which I don't blame you for not liking, another way of looking at this is maybe I have 3 different processes. And I have different computer times. I have programs that can be split up and run in parallel. How do I want to assign tasks to the different things? There's lots of applications to this. It's a little bit easier not to consider the rental harmony problem of how do you divide the rooms and the rent, but to consider the simple thing, I just have this block of resources, and I want to divide it. If the resources were simple, if it was $100 in cash, well, let's do $300 in cash. How should we divide $300 in cash? 100, 100, 100, right? You should all agree that on the basic notions of fairness, this is the fair way to divide, and everybody would be happy with something like this. But if you start to have different resources that different people value differently, it's not necessarily the same thing. So somebody might value the house a lot more, somebody might value the vacation home, someone might value the baseball card. There's lots of different things. And so because different people weight the resources differently, it now becomes an interesting question. And you can actually have a configuration where each person gets more than 1/3 of the total worth, because they disagree on what the total worth is. Now, unfortunately, in problems like this, sometimes your goal is not to maximize what you get. What might your goal be?
Minimize.
Yes, is you get very spiteful. And your goal is, I want to make the other person suffer as much as possible. I want them to be as miserable as possible. Leads to some very interesting mathematics as to how you might rank things. Okay? Let's consider the problem now if we want to divide up these resources. We have a bar. Think of it as a variable density. And different people are going to assign different weights to different parts of it. Yes?
Are we assuming that these resources can't be, the total quantity of resources can't be changed by our actions?
Right, the total quantity is always 1. We can divide it continuously at any point. So for instance, if you have divorce proceedings, you cannot give 1 pound to 3/4 of a kid. You can do that in terms of custody, but you cannot physically divide a kid into 3/4. We will assume that all the assets can be divided continuously. Okay? What do you think it means if we're at the vertex 0? Right, person 0 gets everything. Okay? We've got 3 people in the front row. Person 0, person 1, person 2. Okay, person 0. How do you feel about getting everything?
I'm okay with it.
How do you feel about him getting everything? How do you feel?
Very angry.
Okay, very angry. Okay, so over here we have one person who is willing to vote yay. You know what? On second thought, what if I give you nothing? What if I give you everything? And what if I still screw person number 2? All right, so you'll change your vote? Are you happy with your vote, or do you want to change?
For the sake of demonstration, I will be upset.
Okay. And I assume, are you still very angry? All right. I can't really have a very angry student before we do student evaluations, so what if I give you everything?
No. Change my mind.
Okay, good. And I assume the 2 of you now are upset.
Actually, he and I have made a backdoor agreement, so I'm fine with it.
Collusion becomes a very interesting twist to problems like this. So does everybody agree that in the extreme cases of the vertices, it is clear that in this case, person 0 will be happy and the other 2 people will not be voting in favor? Person 2 will be happy, person 1 will be happy. Let's imagine now we start walking along here. And so one of the reasons I want to do this lecture this way is this is a great way to review all the math we've been doing and talking about the barycentric decompositions and the coordinate systems. We come to an arbitrary point here, which is going to be x0, v0 plus x1, v1. So imagine you're at this point here. I'm going to give x0 to person 0. I'm going to give x1 to person 1, and I'm going to still screw person number 2. You're back to being, I assume, very angry. How do you guys feel? Not bad. What can I do to make you happy about x1? What would you like?
x0 is 0.
You'd love x0 to be 0. Oh, and yourself?
Reciprocal.
The reciprocal. You would love x1 to be 0. Somewhere along these lines, there should be a point of agreement. So at here, clearly, person 0 is happy. As we start moving a little bit away from here, person 0 is still going to be happy. If we start over here and we move away, person number 1 is going to be happy. This is very different than the Sperner problem we've been doing. What's different about the labeling here than the Sperner's problem?
Well, we can walk more continuously. We don't have to try it.
We can always,
Well, yeah.
I mean, we're going to triangulate it eventually, because we're going to use Sperner's lemma.
I mean, I don't think this would be driving that, but
Oh, then don't say it. All right, well,
as the 3 of them demonstrated, different people, like if one person's happiness, it's like her accomplishment. It's not saying that I'm not like happiness. I'm sorry. So someone might be, so person 0 might be satisfied with less than person 1 is satisfied with. You might compare marginal returns to each person that, and you might give more to the person who's doing less marginal returns than
so I'll give an economics example to try to illustrate what I'm doing over here. Does anybody know about the derivative that helped win the Cold War? It's a very famous curve in economics. How many of you have taken an econ class? The Laffer curve. And it's spelled with 2 F's, not an AU. Okay. I'm going to make some very simplifying assumptions because I can do this because this is now an economics lecture. Okay? I'm going to assume that the x-axis is labeled tax rate. I will assume the y-axis is labeled revenue. How much revenue will the government get if the tax rate is 0? 0. How much revenue will the government get if the tax rate is 100%? 0. Right? No one is going to be working if every dollar is taxed away. If I'm at 0 and I increase the tax rate a small amount, what happens to revenue? Revenue will increase. And it will be increasing for a while because it's now going to be worthwhile for people. Well, I mean, it was already worthwhile for people to work. They weren't being taxed at all. Now, of course, we're simplifying a lot of things as you get revenue, what are you doing with that revenue? What is the impact of everything? I'm just trying to look at a very simple model. Revenue is going to go up for a while. What's going to happen at some critical point? Revenue is going to start to decrease. Once it starts to decrease, is it going to go up as you increase the tax rate even more? No, once you've reached a certain critical point and you're losing so much of your money and you say, it's not worth it to work an additional hour. Oh wait, you'll tax me even more if I work harder? It's ridiculous. You're not going to continue to work more. So it'll come down at some slope. Exactly what that slope is, I don't know. There is some critical point, and that's calculus language, where you maximize your revenue. How do you find that critical point? Take the derivative. Set the derivative equal to 0. Now the problem is you have to actually get a good functional form of this. That is extremely difficult to know exactly what the shape of the Laffer curve is and where are you on the Laffer curve. The people who say it's always good to raise taxes, it's always good to lower taxes, almost surely they're wrong. But depending on where you are, you can actually increase revenue by decreasing taxes. And you can also decrease revenue by decreasing taxes. You need to know exactly where you are. But what's nice about this is there's a really nice split. It's going up to a certain point and then down from that point onward. The labeling is very consistent. If you were the federal government at this point, you want to keep increasing taxes. So over here you'd be in the increased tax range, and then over here you'd be in the decreased tax range. Think of those as the 0, 1 labels. When you come back over here to what we're doing with the Sperner's lemma, before, when we subdivided our triangle, we could have any string of 0s and 1s on the bottom. The reason I showed the map of football fans was trying to think of labeling. The football fans, there's some order to the labeling as you would expect from people liking different cities and living near the cities. But you also have these strange pockets. That's very similar to the generic Sperner's lemma. In this case of dividing a resource, we are in a very special case in that how do the labels have to go whenever we partition on the bottom? It's got to go a string of 0s followed by a string of 1s. That's the only logical possibility. And it is some critical point down here where 0 and 1 are indifferent. Now, if we're doing a Sperner label, we can't do a double label. What should we do in that case? I'm sorry?
Pick one.
Which one? Yes, it does. Which one? I'm sorry? Nope. Yes. Why 0? Because it's not 1. 0 is the TA for the class. The reason you would pick 0 is if you think about what we did in Sperner's lemma, we let our function m of x be the first index that differed. So maybe we're doing the smallest thing. Maybe just keep up that consistency, do the smallest label here. If we think about what's going on as we go down here, a general point over here would now be x0 v0 plus x2 v2. What's going to happen as we go up over here? Who's going to be happy down here? Person 0 is going to be happy over here. Person 2 is going to be happy as we fall. We'll reach some critical point where person 0 and person 2 are now indifferent. And we can do the same game over here. So this is very different than what we had before. And then we'll have 2 to 2 like this, 0 to 0, 2 to 2. So if you now think about what's going on at some point on the inside, we're now reallocating resources. And we're saying the 0th person gets x0, the first person gets x1, the second person gets x2. This is very different than the generic Sperner's lemma. Do we know that there exists an optimal allocation? Yes. But when we're trying to do things, if we can make something constructive, do we want to make it constructive? Yes. It's not enough to say, oh, okay, I see the 3 of you are fighting over this. I want to let you know there is a solution to your problem. You can divide it up so that everybody's happy. It was nice talking to you. Right? This is not a useful way to spend your time. You want to actually help people find what's that point. So now when we try to think about this, as we divide things up, we start dividing it up. We keep, so let's see. So now we'll have something like this. What do you think is going to be happening from this corner? What do you think is going to be happening as I move up from this corner? 0 gets less happy, right? We're going to have some kind of boundary line, I think, of 0's happiness. Do you think the boundary line would look like this? And you're going in and out, in and out.
It's going to be the middle triangle.
Do I like person 1 more than I like person 2?
We're going to assume you don't care who gets the other stuff. You just care about yourself. And again, this is not a reasonable assumption in some divorce proceedings. In situations like this, you sometimes gain happiness by other people's unhappiness.
In polygamous divorce proceedings, this would be wildly complicated.
Yes.
Wouldn't our harmony line be like the perimeter of the center triangle? Because we can't hit the middle point, so we can just go around it.
Well, there should be a certain critical threshold of how much you want.
I was talking about between all three.
I'm sorry?
I was talking about between all three.
Oh, between all three. Right, so there's going to be a region here of 0s coming out. There's going to be a region here of 1s coming out. And there'll be a region here of 2s coming down. And yes?
Can you just go over what it means to label when rectangles?
Sure, I have a division of resources where the 0th person gets x0, the first person gets x1, the second person gets x2, and I ask who's happy. If the 0th person is happy, I write a 0. If the first is happy, I write a 1. If the second is happy, I write 2. If multiple people are happy, then I write the lowest index. And so Sperner's lemma assures me that there should be some triangle with 3 distinct labels. Okay. Oh, we have munchkins on Monday. Excellent.
And is happy a binary thing, or is a noun with happy, whoever has the most happiness?
Well, it's just, are you happy with the division? Are you willing to accept this division? So you have to decide, I'm going to give you x0, will you accept it? I'm going to give you x1, will you accept it? I'm going to give you x2, will you accept it? And if it meets your threshold, you'll say yes. Sperner's lemma tells us that there is going to be a way to do this. All right, so we're running out of time. We've got about a minute left, so I'll let you read the rest of the paper in terms of how you make this constructive. But I hope that this is enough. We still have a minute left, guys. I hope this is enough to give you a sense of how we can make this constructive. It's not just a triangle exists where all 3 vertices are different. There's a way to find it. Because we have some logical notion, there's going to be natural boundaries between the regions. If we're on a line over here, we have, right now we've said we've got a certain amount of x0, x1, x2. If I move like this, what's happening? I'm getting more for 0, and I'm decreasing from 1 and 2. So if I move down like this, I can only make 0 happier at the cost of upsetting 1 and 2. So there's going to be very natural, easy ways to move in terms of trying to figure out where to go. So this is the advantage of a division problem like this versus football fans and whatnot. When you look at football fans, there is some interesting geography. It's very similar to the generic case of Sperner. Whereas here, we have this beautiful fact that we've got to have a nice region of 0 coming up, a nice region of 1, a nice region of 2. We will have some regions that are both 0 and 1, where both are happy. And we'll have some regions maybe that are 0, 2, 2 and 1, and we will have a region where 0, 1 and 2 are happy. The interesting thing is that may not be a point. There might actually be a region of configuration space where all 3 people are happy. And they'll all accept it. Then you have to decide which of those do you want to go with.